Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for pre-calculus and college algebra students who need a review on evaluations of functions. And there's actually a lot of subtopics in here, so it's not just evaluating functions like mechanically, algebraically, but we're also going to approach evaluating functions graphically. Most of this video is going to focus around this function that I've handed you here. R of c is equal to a fraction where the numerator is the square root of c and the denominator is the fourth root of 4c squared minus 8c plus 3. Let's talk about components of this function first. So the function name itself is r. That's the name of the function. In coding, for example, we would often name functions like this. And that function, if you've done any coding, takes the floor of a number. In other words, you give it a number like 1.58 and it rounds that down to the nearest whole number. That's what the floor function in coding does. But in mathematics, we do not like having function names that are too long. In fact, we prefer single letter function names, although I really think that's kind of a silly convention. You can actually name your functions as long as you want, right? You don't have to call this little r of c. You could call this RLF of c if you want for, I don't know, real life function. The c is called the argument of the function. A lot of people also call that the input. And just to remind you, the set of all inputs that are viable inputs for your function is called the domain of the function. Let me write that off to the side. So there I've written it. The domain of a function is a set of all possible inputs. Something to let you know about here is that sometimes there is an explicitly defined domain. That is, somebody might come in and hand you this function and they say, by the way, I only want to bother with values of c between, for example, 1 and 5. Now, obviously, I'm not going to restrict this function to only allow inputs between 1 and 5, but if I did, then the domain of this function would be the interval from 1 to 5. Again, I'm not actually restricting the domain of this function that way, but if somebody handed you a function and did give you an explicitly restricted domain, that explicit restriction is the domain of the function. And I call that an explicitly defined domain. Implicitly defined domains are what you're actually facing here. When somebody does not explicitly tell you, hey, C is only between 1 and 5, but instead relies upon you figuring out what the domain is, it's called an implied domain. So if the set of inputs for a function is called the domain, we should obviously have a name for the set of outputs, and we do. The set of all outputs for a function is called the range of the function. Now, this is a very loose definition. To be very honest with you, it is a little more restrictive than that, because you might be handed a function like this, and it might have an explicitly defined domain. So somebody might say, I only want you to worry about values of c between 1 and 5. Therefore, your range for that function would be restricted to the set of outputs corresponding to those inputs. So the range is actually very much dependent upon your domain. It is the set of outputs given the domain of your function. Something else I need to mention before I continue that I didn't even think about as I was putting this together, you should automatically know pretty much all pieces of a function before even watching this video. This is just a review. But one thing that I didn't mention that is kind of critical is actually the definition of a function. A function is a relation between two variables, in this case c, and an output variable, which could be y, but in this case I'll just call it r, which by the way, some people would yell at me about because R is technically not the output variable, it's the name of the function. But whatever. You have an input variable, you have an output variable, and the whole point of it being a function is that every input leads to only one output. That's how you know you have a function. So there you go, in black and white. By definition, a function is a relation where each input leads to a single output. Just to let you know, some people will yell at me a little bit. This is not the most rigorous definition. The reality is that a relation, being a function, could have several input variables. So there are functions of several variables. However, whatever combination of variables you plug in, there's only one output. So if you plug in 5, there should only be one output for that input. Not like I'm going to plug in 5 and I get out plus or minus 27. That would not be a function. But again, it's assumed that you know all of this information about functions. I'm just quickly covering it here. Another thing that I should mention is that a lot of people confuse a function with an invertible function. A function only needs the following. Each input leads to a single output. If the black dots here comprise the set of inputs for some function, for example, and the red dots comprise the possible outputs or the possible range for the function, that means that this black dot can only lead to a single red dot. This black dot can only lead to a single red dot. This black dot can only lead to a single red dot. This black dot can only lead to a single red dot. So each black dot, each input, leads to a single output. But notice the outputs have shared inputs. That can happen. That's totally fine. Nobody is saying that that output has to only come from one input. It could come from many inputs. The only requirement is that each black dot leads to a single output. All right, I think I've belabored the issue enough, so let's go ahead and move on to the problem at hand. Taking a look at it, consider the following function. R of C is equal to, again, all that stuff. Evaluate the function at the indicated values and simplify your result if possible. R of 1/4. Well, that just means take that function and wherever you see a C in it, you're going to replace those C's with 1/4. So let's go ahead and do that. So there we have it. Notice the inputs that were C's before are now 1/4. Most students get that, but still, it's just good to review. Also, you should really simplify this because we were told to. So let's go ahead and take that square root upstairs. That'll be a 1/2. And cleaning up the denominator, we get the following. And now I'll just clean that up a little bit further. And yet a little bit more. And yet a little bit more. Now notice that this is a compound fraction. I'm going to go ahead and multiply both numerator and denominator by the LCD, which is 2 times the 4th root of 4. Technically, this might be able to be simplified a little bit further, but I personally do not mind leaving my answer as 1/2 times the 4th root of 4/5. However, let's pretend as though your instructor requires you to rationalize denominators completely, which I think is kind of silly in this day and age when you're dealing with constants only. But let's go ahead and pretend as though that's your instructor. If that's the case, then I would recommend rewriting this step with rational exponents. And knowing that 5 to the 1/4 is actually the 4th root of 5, I'd like to power that up so that it becomes the first power of 5. And to do that, that means we're going to multiply both numerator and denominator by 5 to a power, where the power, when you add it to 1/4, makes it a first power. And that would be the 3/4 power. Doing that multiplication, and this can be simplified even further. And in fact, what I'll probably do is go ahead and glue that 4 and that 5 together underneath a 4th root, and that can be simplified. And that's about as good as it gets right there. So that's if your instructor requires you to completely simplify or rationalize denominators. I personally don't do that to my students with constants. However, with variable factors, I do. All right, let's take a look at the next problem. Remember, this is our function right here, and we're being asked to evaluate that function at t plus 1. This is called a symbolic evaluation. I just wanted to cover it so that you know how to do something like this. So we're going to take our original function, instead of c's in our original function, we'll replace all of those c's with a t plus 1. And if you saw my screen kind of zoom in and zoom out a lot, it's because I always have to recheck what the function is as I go through and do these problems. This is not completely simplified, by the way. So what we want to do is go ahead and simplify that denominator. That's just some old school algebra simplification there. Now we're going to do some more distribution. And combining like terms in that denominator. Well, that denominator cleaned up a little bit better than I thought it would, but there you have it. You could rationalize this denominator if you are forced to. Just giving you a heads up, when you do rationalize a denominator like this one, it's a little bit easier to do this type of rationalization when you have a radical that's something other than the square root. It's a little bit easier to do it when you write it with rational exponents. And that's because you can actually see what you're going to have to add to that power in the denominator to force it to be a power of 1. You have to add 3/4 to it. So I'm going to multiply both numerator and the denominator by 4t squared minus 1 to the 3/4 power. Now I've run out of page here, so I'll just move to the right. In fact, maybe I'll move this thing up. And let's go ahead and do that multiplication. In the numerator, you're not going to glue those together, at least not yet. In the denominator, those obviously are the same base, so their powers add. That will be 4t squared minus 1. Now, honestly, to me, this is clean. Although I have to say, probably right back here is where I would have stopped. But again, if your instructor forces this issue, then fine. Although that would be ultimately very cruel. In fact, maybe I don't want to go further with this because all you're going to do is get lost in the weeds on this one. But this is a good kind of simplification. Although if you're one of my students, the highlighted piece right here is probably where I would have stopped because that's completely done. All right, continuing to the next page here, we have a part B for what values of C, remember C is the input, so what values of the input is R of C equal to 0? In other words, when is the output equal to 0? And essentially what we're being asked to do is to solve 0 is equal to, well, the function. And the only way that a fraction, like this one on the right-hand side, can become 0 is if its numerator is 0. And the only time the numerator is 0 is when the square root of C is 0, which implies that C itself must be 0. Now, before I box that up and say that's the answer, you should double check that you can plug C into that denominator without the denominator turning into 0 or having issues. So just visualize with me, if you allowed C in that denominator to be 0, you'd get 0 minus 0 plus 3. That's critical that we talk about that because if that wasn't a plus 3, but instead a minus 3, there'd be an issue, right? If you tried to plug in 0, you'd have the fourth root of negative 3, and that is illegal. That's a fourth root of a negative number or an even root of a negative number, which means there is going to be an imaginary answer. Luckily, that was not what we were handed, but that's just something you have to take into consideration as you move forward in mathematics. You start fine-tuning all the details that you've learned in the past. All the problems become a little more complex, and you have to think about several things at once. That is what stepping through mathematics is like. So we've appropriately thought about that condition, and we're still okay. So this is the value of C for which R of C is equal to 0. Part C in this problem is solve R of C is equal to 1. So it's very much like part B, but in this case, we're going to let 1 equal our function, and we're going to solve that. So zooming in here, to solve this style of equation, you're going to go ahead and multiply both sides by the denominator, basically what I've heard students call fraction busting. You're just multiplying both sides by the LCD. There is something stated here that you have to be careful about. There's going to be a domain issue, but we can check that when we get to the end. So you get to this point right here, and you see that you have a radical equation, And so your first step is really to square both sides. We've isolated a radical, whether you consider the left or the right-hand side the radical you want to isolate, doesn't matter to me. But let's pretend that you say, okay, I've isolated the square root of c, so I'll square both sides to unlock that c. Well, once you square both sides, it actually doesn't completely obliterate the radical on the left-hand side. If you square both sides, well, the right-hand side is definitely going to be c. But the left-hand side, well, that's something to the 2/4 power. In other words, it's a square root still. So that means we still have to square yet again. And something that I've mentioned to my students in an in-class environment, and I often forget when I'm lecturing online, is that every time you're given an equation and you decide during the solving process to square both sides, you might be introducing what are called extraneous solutions. Whenever you square both sides of an equation, you run the risk of introducing extraneous solutions. Same thing with when you multiply both sides by a statement involving a variable. So like when we multiply both sides by the 4th root of that ugliness down there, we likely introduced some incorrect solutions. So we are going to have to definitely check our answers in the end. But let's go ahead and square both sides on this equation. And now we're just going to subtract c squared from both sides, and you have a beautiful quadratic equation. We could see if that factors. Nope, it doesn't factor. The reason why I know it doesn't factor is while 3c times c would be 3c squared, and let's see, negative 9c and plus 1c would give me a negative 8c. Unfortunately, positive 1 times a negative 3 would give me a negative 3, not a positive 3. So this does not factor. By the way, that wasn't the only effort to factoring, but as I again tell my students in class, I spend around 20 seconds trying to factor, and if I can't factor within 20 seconds, I immediately then go to the quadratic formula. The quadratic formula should not be your first choice. However, it's a definite good backup. Before I perform the quadratic formula to see if there is a solution here, I'm going to find the value of the discriminant. Just to remind you, the discriminant when you're given a quadratic equation is b squared minus 4ac. It's the stuff that's under the radical when you're going to solve a quadratic equation. If that stuff is negative, there's no real solution to this quadratic equation. However, in this case, this is non-negative. We still need to compute it, so I might as well just finish this out. We needed to compute that anyway when you're using the quadratic formula. So that's our quadratic formula right there. It's 8 plus or minus, let's see, 4 times 7, 2 root 7 all over 6, and that reduces down very nicely to 4 plus or minus root 7 over 3. But remember what I said earlier. When you start squaring both sides of an equation or multiplying both sides of an equation by variable expressions, you've got to check your answers. The other thing I should mention here is I wrote down x, and the reality is it's c. So let's go ahead and look back at the original function to determine if either of these solutions are viable. The original function was square root of c divided by the 4th root of that ugliness. Well, one thing I can tell you very quickly is that the square root of c requires c to be non-negative. Looking at this solution, neither of them are going to be negative, so I don't have to throw one out yet. But I definitely think that this is one of those problems where you should be able to quickly grab a calculator to check your work. Remember, the function is actually just this right-hand side here. So let's go ahead and just grab a calculator and check to see if either of these solutions work. I'm going to go ahead and use Desmos here. I'll showcase how to do that.
So here we are in Desmos, and I'm going to go to the scientific calculator because that's all we really need for this part. I'm going to type in the function. Notice that I used different function names because I really don't care. This is just within Desmos. I'm not really that concerned about it. Also, I'm using x as a variable. Again, we're in Desmos. I'm not too concerned about that. Now we're going to check our answers. Remember, we want the function to turn into 1 when we plug in these answers, and our answers are supposedly 4 plus or minus the square root of 7 over 3. You can see that when I plug in 4 plus the square root of 7 over 3, that turns into 1. As well, you can see that it turns into 1 when we plug in the minus root 7 over 3. So both answers work.
All right, now that we're back, let's take a look at part D here. Evaluate each of the following and simplify if possible. Discuss the differences between the answers and common mistakes you think other students might make. Well, first thing I should do is rewrite the function. So I've done that off to the right-hand side there. Now we're going to take a look at r of c squared. What does that really mean? Well, it means that you're going to take your function and you're going to square it. That's all. And our function, remember, was the square root of c divided by the fourth root of 4c squared minus 8c plus 3. Again, we're squaring that. The square can be applied to both numerator and denominator here. In this case, when you square a square root, that becomes just c. When you square a 1/4 power, it becomes a 1/2 power or a square root. And that's about as good as it gets. That's what r of c squared is. So far, nothing big. What are the common mistakes I think are going to happen? Generally, students don't do too terribly on this unless they're new to algebra, and then they end up only applying the square on the c, and they plug in c squared. But that's not what the square is touching. It's touching r of c. So you're going to take your function and then square that. Let's take a look at the second one, and lo and behold, there is the r of c squared. So that just means take your function, which was the square root of c over the fourth root of 4c squared minus 8c plus 3, and instead of plugging in c's, you're plugging in c squareds. So plugging that stuff in, it looks pretty easy, looks like somewhat simple, but I am going to showcase something that students often get wrong. So up to this point, most students are pretty solid, but then students will often say that this guy is equal to c. I'm going to use x instead of c's here just because I don't want to convolute the problem. The square root of x squared, or maybe I should even write it this way, the nth root of x to the nth power is equal to one of two things: x if n is odd, and the absolute value of x if n is even. It's equal to x if n is odd because the odd root of an odd power, well, odd roots can return positive or negative numbers, so that doesn't matter. So that's why the odd root of x to the same odd power is just x. However, if it was the second root of x squared, second roots never return negative numbers. So first and foremost, I know the answer, or what this simplifies to, is not going to be negative. And let's make it a little more realistic and say, well, what if we were looking at the square root of a -3 being squared? Would you say that's going to return a -3? I hope you don't, because that can't return a negative number. It's going to return +3 because when you take -3 here and square it, the negativity disappears. It becomes a +9. You take the square root of 9, that's going to be 3. So this is a good solid example as to why even roots of a value to that same even power are going to return the absolute value of the argument of your even powered function there. So going back to our original problem, this could have been written as the absolute value of c. Now I almost went and made the faux pas here after I went through all that discussion. I was going to say we could rip the absolute values off of this, but actually we can't. The reason why we cannot is because what we're plugging into our function is c squared. And so nobody told me what c was. C could have been a -3, right? And so when we take -3 and square it, as we did over here, and then we take its square root, it returns +3. It returns the absolute value of that -3. So I do actually have to keep these absolute values on here. This is a significant struggle for students to kind of comprehend, but the reality is when you're taking the even root of a variable to that same even power. It's going to return the absolute value. So let's see. We looked at r of c squared. Then we looked at r of c squared. Notice how I said that differently. Now let's take a look at r of 2c. Notice how I'm just changing where the 2 is positioned. So if I look at r of 2c, well, here's r of c right here. All I'm going to do is replace all the arguments with a 2c. And really, that doesn't trip people up. All you have to do here is just simplify this expression. And that's about it. There's not much else you can do there. I would say that it would be beneficial to see if that was a perfect square in that denominator. And I haven't mentioned that through any of the previous examples, but that was only because it wasn't a perfect square, and it still isn't a perfect square. It's a very rare situation that happens in, but just in case, look for perfect squares. And that does it for this page. Let's go ahead and move to the next page. State the domain of the function r using interval notation. So I wrote the function off to the side. I'm going to look at both numerator and denominator separately. So the domain is going to be restricted implicitly by these even indexed radicals. For example, in the numerator itself, the fact that we have the square root of c implies that c must be non-negative. So this is my first domain restriction on the function r, but it might get tighter than that. Going back to the function, now I'm going to focus in on that denominator. The denominator not only cannot be 0, but the argument of the radical, which we would call the radicand, cannot be negative. So that implies that 4c squared minus 8c plus 3, it can't be 0 and it must be positive. So that is, it has to be greater than 0. Now you should have just finished a set of videos that I've put out on solving quadratic inequalities. If you have, then you know what you're going to do here is try to factor that left-hand side. And it definitely factors to this here. You can see you get 4c squared from that. You get, let's see, a negative 6c there, and you lose another 2c, so that's a negative 8c. And then finally, plus 3. So this is how it factors. I'm going to use the graphing method for solving this quadratic inequality. I can easily see that the x-intercepts, or in this case, c-intercepts, of that quadratic expression on the left-hand side are 1/2 and 3/2. And I also know that if I were to graph that left-hand side, it's a parabola opening upwards. Just as I said in my video on solving quadratic inequalities, nobody's going to judge you on your graph here because that's not what you're technically being asked to do. So I'm just going to quickly scratch this out, and you can see this parabola, which corresponds to this quadratic expression, is above the height of 0 on these intervals right here. And we want it to be strictly above, so we're not going to include 1/2 and we're not going to include 3/2. So remember the question that we're answering here, we want to know the domain, and we're requiring not only that c be greater than or equal to 0, but we're also requiring that c be in these intervals here that I've highlighted. So let me go ahead and draw down all of our restrictions. Remember, c can be greater than or equal to 0 and less than 1/2. So in this shaded region, c is less than 1/2, but still greater than or equal to 0. Also, in this region, c is greater than or equal to 0 and greater than 3/2, which is exactly what we want here. So the overall solution set for this, or in other words, the domain of our function, is going to be the half open interval closed at 0, ending at 1/2, not including 1/2, union with the open interval 3/2 to infinity. That is the domain of R. Notice how many skills we're engaging here when we work with functions. We solve quadratic inequalities. We have looked at some obscure algebra involving the square root of c squared, stuff like that. A lot of this stuff gets engaged when you're working with functions. All right, let's take a look at the following graph. And this graph just consists of half open intervals. That's what this would be called, a half open interval. Half of it's closed, half of it's open. Discrete points, that would be like this guy right here. And vertical asymptotes. This red vertical line is a vertical asymptote. And that's supposed to be the number 1. I just didn't complete it out there, but that's the number 1. And we're going to use this graph to state the domain and range of this function. And it totally is a function because it passes the vertical line test. You can put a vertical line anywhere on this, and no matter where you place the vertical line, it strikes the curve at most once. That's the vertical line test. You should recall that from your prerequisite algebra. So let's talk about the domain first, then we'll talk about the range. So the domain consists of all x values that lead to y values on the graph. For example, if I were to plug in x equals -3, it leads to a y value, doesn't it? And if I were to plug in x equals -2.5, that totally leads to a y value as well. If I were to plug in x equals -2, it leads to a y value. If I were to plug in x equals -1, that leads to a y value, and so on and so forth. Plug in x equals 0, it definitely leads to a y value. I just have to get it on there. If I plug in x equals 1 though, that's a problem. There's no y value associated on the graph with x equals 1. So x equals 1 is not in the domain of this function. I could plug in x equals 1.5, for example, and I could plug in x equals 2. So judging from what we've written here, the domain goes from -3 to 2. That's the set of x values I can plug in, with the exception of x equals 1. I can include -3 in my domain because I can plug it in, but I cannot include the x value of 1. And I skip over that 1 and start on the other side, and I can plug in any x value between 1 and 2, including 2, by the way, because when I plug in x equals 2, it leads to that height right there. Now let's talk about the range. And if you haven't noticed, I always start from low to high, so the lowest y value this curve will ever take, well, it keeps diving down forever and ever and ever. So if it dives down forever and ever, then the range goes all the way down to -infinity. Now let's start climbing. You can see there's a y value here and a y value there that hits the curve and a y value there, and so on and so forth, all the way up until a height of, this looks to be a height of, what do you think that is? Like a 1.2? So let's just say it is a 1.2. So the range goes from -infinity all the way up to a positive 1.2. Zoom in and write that down. It's an approximation, but whatever. It includes 1.2 because the y value of 1.2 corresponds to the x value of -2. I am again just approximating that, but I think that's pretty okay to do that, to say that this point is -2, 1.2. I'm okay. As you go up above this blue line here, let's say we hold over right here. If you look to the left or to the right, there is no function value on my curve to the left or to the right. So I cannot include that y value in my range. However, at y equals 2, definitely I have an x value associated with it. That would be x equals 2. So at x equals 2, y is 2. So what I'm going to do, that's called the discrete point. I'm going to union onto this interval the discrete point 2. That's y value of 2, by the way, not an x value, a y value of 2. Your range is just a set of y values. As you continue to climb, you go beyond y equals 2, you look left and right here. There's no graph, so I can't include that y value. You climb a little bit more, you look left and right. Again, there's no graph, so you can't include any y values there. You get to a height of 3, and it looks as though the graph exists at y equals 3, but it doesn't. That's an open hole there. So the graph doesn't actually pick up in y values until after you get beyond y equals 3. What that basically means is that my range picks back up, so I'm going to union at 3, but not including 3. And from that point forward, as I look left or right, there's always a function. There's part of my function that exists. No matter where I'm standing, I have a function somewhere to my left or right. So from that point forward, the graph just climbs forever. So this is a good example of how you would write ranges with discrete points. Not very common actually, but it's a good example of that, so why not? Again, it's not super common to have that discrete point in a math class, but it does happen. Finally, let's do a word problem, an application. This is one of my favorite applications. It actually exists in calculus quite a bit. According to Einstein's theory of relativity, the length of an object is a function of its velocity v with respect to an observer. For an object whose length at rest, relative to us, is 130 meters, the function is given by this. So they hand us a function. This represents the length of an object, which has an initial length when it's just sitting on the ground and we're just looking at it, of 130 meters. But its length will adjust if it starts moving toward, away, side by side, whatever it is. If it starts to gain a velocity, its length actually does change. And I don't mean like, oh, visually its length changes. I mean, its length actually changes. In that function, you could see L of v is equal to 130 square root of 1 minus v squared over c squared. Well, v is how quickly the object is moving. But what's c? Well, c is the speed of light. You don't actually need to know what it is for this problem, so I'm not going to tell you what it is. You can actually Google that. It's very easy to search for the speed of light, but it's not needed for this problem. So in part A, we're being asked to determine the values of L of 0.5c, then L of 0.75c, and then L of 0.9c. I'm a huge fan of students interpreting what things mean. So what does 0.5c mean if c is the speed of light? Remember, what you're plugging into this L, this length function, is a speed. And so what this represents is an object moving at half the speed of light. So let's plug that in to our length function. So there we go. I plugged in a 0.5c. Now I'm going to go ahead and clean up, do some arithmetic here. Notice that the c squareds cancel. And this becomes 130 times the square root of 0.75. Now, because this is an application, it is kind of implied that you can use a calculator here. This is going to be roughly 112.6. And let's remember what this value represents. It represents the length of the object. So this is 112.6 meters because that's what the original object was measured in, was meters. So this object, which was sitting at rest and was 130 meters in length, zooms away from us or towards us or from side by side, whatever it doesn't really matter. It starts moving. The faster it goes, the shorter the object gets, not just visually, but physically. Now let's take a look at the next part, L of 0.75. Once you got the first part, the rest is just kind of a rinse and repeat. Notice in both cases, you end up with c squareds canceling. Also notice I did not bother squaring 0.75 because I know I'm going to grab a calculator anyway, so I'm just getting this down to a form that I can plug into a calculator. And that's this form right here. And that's how long the object is if it's going 75% of the speed of light. It shrinks down to 86 meters in length. Again, rounded there. Let's see if the object goes to 9/10 the speed of light, or 90% of the speed of light. So we get all the way down to that spot right there, and I just grab a calculator, and this object is approximately 56.7 meters in length. And part B is saying, how does the length of an object change as its velocity changes? And the answer to that is as velocity increases, length decreases. That is physics. That is awesome stuff right there. That kind of does it for this video on a reminder of how functions work, evaluating functions, really things you need to think about when you're handed a function. You're always going to think about domain. So you're going to think about like what you can plug in, what's legal to plug in. You need to know how to evaluate functions and how to evaluate them symbolically, which means plugging in variables. You should be able to do that. So this video kind of covers that theory. I hope to see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't